Okay, let us see something nice and deep with some mathematical analysis. Let us continue with our question of when exactly do we see a connected graph as we keep putting edges. So the question is this, the same question that we have been discussing so far. Assume there are 100 people, or let us say n people, n is equal to 100 here, a particular example, okay. There are n people here. If you put all the edges, what is all the edges? N choose 2, or let us say 100 choose 2. If you put all the edges, obviously the graph becomes connected. Now when you put all the edges and remove just one edge, it remains connected. If you keep plugging out edges one at a time from this complete graph of n choose 2 edges, there is a time when it becomes disconnected. I repeat, take 100 nodes, put all possible edges between any two nodes, which happens to be 100 choose 2, and from this you start removing one edge at a time, remove and then throw it. Keep doing this, you will finally get a disconnected graph somewhere at some point. The question is the investigation of when exactly you will get a disconnected graph as you keep removing edges. So complete graph, no completely disconnected graph, complete graph means all edges, completely disconnected graph means absolutely no edges. As you keep removing edges, you come closer and closer to this, there is a point when the graph becomes disconnected, right. So I am going to use the word totally disconnected, which stands for no edges at all, and then I am going to say totally connected, which means it is a complete graph. Zero edges, no edge at all edges, n choose 2 edges, okay. As you keep removing edges, you will observe that there is a point when the graph becomes disconnected. What is that point? Should you remove half the edges, or only a few edges when removed will make the graph disconnected, or should you remove a lot of edges? This question is same as take no edges, keep putting one edge uniformly at random, when exactly will the graph become connected? So I will write this down for clarity sake. Given n nodes, as one keeps adding new edges, I use the word uniformly at random. By this I mean I do not have any preference for the edges, I keep putting edges uniformly at random, randomly basically. As I keep adding edges uniformly at random, when will the graph become connected? Now a question like this does not have an answer. We always say mostly if you put so many edges it becomes connected. What do I mean? What do we mean by this? If you say I need to lose weight, I need to lose 5 kilograms of weight, you will say okay, then you should start running half an hour a day for the next 1 month. I mean, this is just some sort of a guesswork, and you will say on an average if you run half an hour a day, in let us say 1 month's time you probably can lose 2 to 3 kilograms of weight. I am not a dietitian, I am not a exercise expert, I am just telling you as an example, right. Similarly, I am asking this question, as you keep putting edges, what do you guess will be the number of edges that it takes for you to make the graph become connected? Let us answer this question with a small observation. Okay, I will answer this question by asking this question: when will the graph not have an isolated vertex? To answer this question, I am asking another question. I'll ask you this question: as you keep putting edges, when is the time when you do not have even a single point without edges? What do I mean by that? So let me take 1, 2, 3, 4, 5 vertices here. As you know, how many possible edges can you put? Little bit of observation tells you 10 edges totally. Let me put one edge. When I put one edge, this is isolated, this is isolated, this is isolated, this was isolated, does not continue to be isolated because you have put an edge. Now I will put another edge, let us say this. There are 2 isolated vertices now, still 2 isolated vertices, only one isolated vertex, only one, none. There are no isolated vertices right now, correct? After putting 1, 2, 3, 4, 5, 6 edges, isolated vertices came to an end. But then I should be putting these edges uniformly at random. I should not try to put edges just in order to make the graph appear connected without any isolated edges. Please note, you cannot have isolated vertex, sorry. You cannot, you can continue to have an isolated vertex by simply putting all possible edges within the remaining vertices, not touching a vertex, that is always possible. But the question is, uniformly at random when you start putting edges, when does the graph become connected? Let us answer this question. So we all have seen this result which says 1 plus 1 over n whole to the n is, as n becomes bigger and bigger, this quantity is between 2 and 3. This is called E, we all have seen this, it is some basic calculus, limits basically. As n increases, 1 plus 1 by n whole to the n becomes E. For example, if n is 10, 1 plus 1 by 10 which is 1.1 to the power of 10, 1.1 to the power of 10 is around 2.7 which is E's value. 1 plus 1 by 20 whole to the 20 is roughly equal to a number between 2 and 3. So it is observed that this is the limit of this is a constant. A little bit of observation says, in fact we all have observed this in our 11th 12th standard mathematics, this is 1 over E. Do not worry much if you do not recollect these things. All I am trying to say is 1 plus 1 by n whole to the n, as n becomes bigger and bigger, becomes a quantity between 2 and 3 which is E. 1 minus 1 by n whole to the n, let us say n is 10, then this becomes 1 minus 1 by 10 which is 0.9, 0.9 to the power of 10 is 1 over 2.7, okay. As n is very bigger, it becomes very accurate. Now we are going to use only these two things, okay. What is the probability, let us get back to this question, what is the probability of you having a vertex V becoming isolated, okay, when an edge is included? There are n nodes, you put one edge and V, a particular vertex V is isolated. What is the probability? What do I mean by this? Look at this. Here are 100 nodes, this is my vertex V and you put one edge. What is the probability that V continues to be isolated when you put one edge? In this big graph, when you put an edge where no edges are there and you put an edge, it is very unlikely that this edge will fall on V. It will be some alpha and beta, some two vertices, it may not be V. What is the probability that it is V? There are 100 people, V is one of them, you choose 2 people to put an edge, what is the probability that it is V? It is 2 by 100, simple observation. Maybe you may want to pause and think for a minute why that is true. I am assuming that you know how it is 2 by 100. So when I put an edge and that edge not being on V, on a graph with n vertices is 2 divided by n. As I keep doing this, you know, the probability of we having rain today, if it is let us say 1 by 4, the probability of it not raining today is 3 by 4, correct. So let me say probability of V not being isolated is 1 minus 2 by n when you put one edge. You see, probability of it raining today, if it is 1 by 4, probability of it not raining today is 3 by 4. The probability of not raining today and tomorrow is 3 by 4 into 3 by 4. The probability of we not seeing any kind of rain happening today, tomorrow, day after is simply product of 3 by 4, 3 by 4, 3 by 4. Again straightforward concept of probability, right. So probability of V not being isolated after K edges being put is 1 minus 2 by n times 1 minus 2 by n times 1 minus 2 by n, so on k times, right, so on k times. So we saw that the probability is 1 minus 2 by n whole to the k, the probability of V not being isolated after k edges being put. Now let me ask this question, when k is equal to 1, the probability of V not being isolated is 1 minus 2 by n whole to the k, k is 1, correct. If k equals to, this will be 1 minus 2 by n whole square. If k is 3, it will be cube. If let us say k is equal to n, then this is going to be 1 minus 2 by n whole to the n. Observe this, let me observe this. What am I saying? When we include n edges, which means k equals n, the probability of V not being isolated is 1 minus 2 by n whole to the n, which is 1 minus 1 divided by n by 2. 2 goes down and becomes n by 2 whole to the power of n. I will do a small fine tuning here. I divide this by 2 and multiply it by 2, okay. The usual trick that we do in mathematics. If something does not look very nice, we make it appear nice by multiplying something on both sides, multiplying and dividing by the same number, adding something on LHS and RHS, we know those tricks. So I am writing it so that this appears like something that we know already. In place of n we have n by 2, 1 minus 1 over something to the power of the same thing is 1 by e. So this is 1 by e, which means is equal to 1 over e, this is 1 by e, 1 over e square. What do I mean by this? E is a number between 2 and 3. Okay, let me say 2, E is 2. If E is 2, then the probability of V not being isolated is 1 by 4. There is a quarter probability that, pause and think what I am saying, there is a quarter probability 1 over let us say 2 square or 2.7 square actually, whatever, a constant. There is roughly quarter probability that when you put n edges, on n vertices you put n edges, there is some decent probability 1 by 4 that your V is not isolated. Okay, it's a very small probability, but then I will do a small trick. I will take k equals n times log n. Okay, don't ask me why am I taking n equals log n, just for fun. You can take whatever you want, alright. There is a reason why I am taking it this way, but for the time being you assume that I am taking something slightly more than n, which is n log n. If I take k equals n log n, the probability of V not being isolated happens to be, let me rewrite this, 1 minus 1 over n by 2, this thing. Instead of n I should put n log n here, n log n here, n log n here, and here this becomes same thing. I repeat, 1 divided by n by 2 whole to the n by 2 times log n. We know this part is, we saw it's e, correct. So there is a 2 here, 2 here, this becomes 1 over e square times log n, which is 1 over e to the log n, let us say whole square. I have just taken log here and put to that side, which is equal to 1 over, we know e to the log n is n, 1 over n the whole square. Let me take a minute and stare at this and observe what just happened. The probability of a vertex V becoming isolated after including n log n edges is this. I repeat, the probability of a vertex V becoming isolated after including n log n edges is 1 over n square, which means if you take a graph with 100 vertices and if you only put 100 log 100 edges in that graph, then you will find a vertex V isolated with 1 over 100 square probability. Okay. So by that I mean 100 node network, V is isolated after putting 100 log 100 edges. The probability for this to happen is 1 over 10,000 is what my observation says. My observation says when you take 100 nodes, a vertex V is isolated with a very small probability if you put 100 log 100 edges, which means when you take a graph G with n nodes, you take a graph G with n nodes, by just putting n log n edges, with a very high probability you will not have any isolated vertices. Not having isolated vertices does not guarantee you of a connected graph, but then not having given an isolated vertex but the graph is disconnected is very unlikely. I told you before, correct? You cannot have two components. You cannot even have one disconnected vertex because it is very small a probability. Now this tells you that as you keep putting more and more edges, very soon the graph becomes connected. When you put n log n edges, the graph with a very high probability does not have any isolated vertices, does not have any isolated components, there is no isolated vertex. Having an isolated component is very unlikely, correct? With a very high probability the graph is connected when you put just n log n edges. So we saw if one puts only n log n edges in a graph, the graph becomes connected. You see what is n log n? Given a graph with, let us say, 1 million nodes, 1 million times log 1 million, so many edges suffices to make the graph become connected. A point to note, log n means number of digits in n. So you are not multiplying n by a big factor here when I say n log n. By n log n I mean something almost as good as n. So if you have n number of vertices, by putting just a few edges, as many as the vertices itself, n times log n, you achieve connectedness. Now we saw the theoretical framework for it. Do not worry much about all the proof that I gave you, it is not very important. I just gave it for completeness sake. All that you need to know is the following. Let me go slowly. All that you need to know is this: given n nodes, you keep putting edges, you keep putting n log n edges, then the graph becomes connected. How true is this statement? Whatever I wrote on the board may not be true. The mathematical statements I have derived is in no way a validation for what is going to happen if I am going to program and see it. Maybe or may not be, I do not know, I am at least not convinced. So let us do one thing, let us take our laptops and try to write a piece of code and then check if it is really true or not.